Welcome to Lecture 11. We are going to continue on with our stoichiometry discussion in this lecture. We're going to add the concept of limiting reactants, um, which can be explained by many different analogies. But let's just talk just for a moment in review about what we talked about in the last lecture. And that is if we have a chemical reaction, the coefficients in front of the products and reactants can help us to determine amounts given one amount. So it's a proportion, it's a recipe. You never change the coefficients once you've written your balanced chemical equation, and that's your first step in a stoichiometry problem. In the problems that we did last time, we would start with, first of all, we started off with amounts in moles. And then the second step is, if you're not in moles, get there, because these coefficients also mean, in addition to particles, they mean moles. So it's 1 mole of A plus 2 moles of B to give 3 moles of C and 4 moles of D. If I want to know how much C am I going to make if I start off with 2 moles of A, and I'm being careful in placing my amounts underneath the species or the substances that I'm being given information about, and the one that I'm being asked a question about. So I'm already in moles, so the only time I use the coefficient is in this moving step. As I go from one to another, and it doesn't matter direction, I can be on the same side, doesn't matter. I'm always going to take that amount in moles and multiply times the coefficient of what I'm moving to over what I'm coming from. So I will make 6 moles of C. If I wanted to know how many moles of D, I can either go from C or from A. I'll get the same answer. Showed you that in the last lecture. I'm going to go from C since it's close by. I will take those 6 moles of C times the coefficient of what I'm moving to, the 4, over what I'm coming from, which is the 3. And 6 times 4 is 24 divided by 3. 8 moles of D are made. Now the only difference in the type of problem that you might see is if you are not given amounts in moles and you are asked for an amount that's not in moles at the end. I explained in the last lecture that I always think about these problems in terms of the setup as a box. So if I were given 4 grams of B is what I'm starting with, and I want to know how many grams of D I'm going to make, well, my first step is to get into moles. And I am going to use the periodic table to do that using our old mole chart. 4 grams times, I'm going to be dividing by the molar mass from the periodic table, okay, for whatever B is, to get into moles. Then I will use the coefficients. In this case, it would be times 4 over 2, okay, and I would have my moles of D, and then I would do another periodic table step. So here's the box, okay, box, where I then take those moles of D and use the mass from the periodic table to switch it back to grams. I do not use the coefficients on these vertical steps. Okay, we didn't before. That's a mole chart step. The only one I'm using the coefficients on is the horizontal step, the moving step. And that is the basics of stoichiometry. The only thing that's going to change with what we're going to talk about today is often we have a limiting reactant situation. So let's talk about my analogy there, and then I will use this same example to pretty much chart out. It's one additional step. And that is step 2B on the steps provided in the last lecture. So I've used many different analogies. This one is cars. If I have 8 car bodies and 48 tires, how many cars am I going to make? Well, I think we can talk about it in terms of an equation. That's what we would do if it were chemistry. So 1 car body, if we do this systematically, plus 4 tires equals a car. Okay. Well, if I have 8 car bodies, how many tires am I going to need? I know you can do this in your head, but this is how we're going to do it, as a chemistry problem. Well, 8 times 4 over 1, right? I'm moving from car bodies to tires to figure out how many tires I need, and 8 times 4 is 32, okay? So 32, 4 over 1, 32 tires. So I have 16 tires left over. Now, it's as easy to conceptualize with tires and car bodies, but if I were doing it the chemistry way, we haven't done that entirely yet. This is what I would do. I would take let me erase my amounts here. Well, I need to left the 8 there. I will take the 8 and the 48 as my amounts. I will divide the 8 by its coefficient. So I urge students not to write that number down because you're not going to use the number you get when you divide by the coefficient. It just tells you which one is smallest. Okay? In the case of this example here, car bodies is limiting. We already know that. I cannot make more cars because I don't have enough car bodies. I've got plenty of tires. So we call this the excess. Okay? Well, the way that you do it when it's not so obvious is you take the amount in moles, of course. So that's why this is step 2b. 8 divided by 1 versus 48 divided by 4. 48 divided by 4 is 12. 8 divided by 1 is a smaller number. That tells me this is the limiting reactant. You must use the limiting reactant or you will be promising somebody more cars than you can make. If you are given in chemistry, using this example that I have written up here at the top, if you're given in moles, then it's easy. You're already there. You can divide by the coefficient. So if I have 2 moles of A and 4 moles of B, 2 divided by 1 versus 4 divided by 2 is actually the same number. This is the exact stoichiometric ratio I need. So there is no limiting reactant, okay? Because I got the same number when I divided by the coefficients. So let's change it. Let's say I have, let me just erase, okay? So this is the new step. Divide by the coefficient after you're in moles, and that tells you which one is limiting. And then you go from there and everything's the same. For those of you who are wondering how it all works. So if I have, let's make it big. Let's say I have 16 moles of A and 46 moles of B. All right? 16 divided by 1 versus 46 divided by 2. 46 divided by 2 is 23. A is limiting reactant. I must use A to figure out anything concerned with products. I used to, when I taught high school, I used to make it s'mores day when we talked about limiting reactants. And I would tell the students to bring in, they would have to organize it, the graham crackers, the chocolate, and the marshmallows. Well, I knew they wouldn't get the proportion right. And I knew they'd probably forget, so I usually backed them up with some supplies. But I, get to teenagers with food every time, and I would drive, home the idea of proportion, this limiting reactant. So most of the time, it was usually chocolate that was limiting, and then we'd have tons of marshmallows and maybe graham crackers left over. All right, so here's a little problem here, and it is before reaction started, after reaction is completed. So we could, looks like we are taking one of the open ones and one of the closed ones. We could count. We're not going to do that. This picture is just to drive home the fact that when this is completed, I see all of the open circles have been used up. Therefore, it is the limiting reactant. I see lots of these dark circles, I'm sorry, not that one, that left over, so it is the excess. Now, there, if you look, I'm going to click on these two links here in a moment. If you look in your book, and I know there's a lot of students who are, who do rely on that textbook, they're going to show you the long way. They're going to take the amounts, they'll switch them into moles, they'll essentially do the whole problem twice, okay, to figure out which one gives you the smaller amount of product, and that's how they do limiting reactants. My way works every time, and it's so much shorter. Divide the moles by the coefficients. That tells you which one is smallest. Don't use the number you get when you divide. All right, let's go back to these links, and let's click on, I can't remember what they're for. Oh, that's just for the diagram. So back to the notes. I try to reference my diagrams. This is a flash, though. Let's do that one.
Nitric oxide, NO, is produced when atmospheric nitrogen and oxygen react at high temperatures in an automobile engine. Once released into the atmosphere, nitric oxide is quickly oxidized to nitrogen dioxide, NO2. Nitrogen dioxide is a toxic brown gas. Much of the brown haze present in photochemical smog is due to the presence of nitrogen dioxide. The left side of the two-bulb vessel contains nitric oxide gas, NO, and the right side contains oxygen gas, O2. Click on one of the buttons to choose the number of molecules of NO you would like to react with the number of molecules of O2.
All right, so we have 3 different scenarios here, and we're going to go through them. And because I like these visual animations, I think they're helpful. Oops.
Nitric oxide and oxygen gas are reacted in a 1-to-1 mole ratio. There are 4 molecules of NO in the left bulb and 4 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2 producing 2NO2. 4 molecules of NO are reacting with 4 molecules of O2. The 4 NO molecules require only 2 O2 molecules for reaction. Note the 2-to-1 mole ratio in the balanced equation. Therefore, 2 O2 molecules remain after reaction. The reaction stops once the nitric oxide gas runs out. NO limits the amount of product that can be formed and is therefore called a limiting reagent. Oxygen gas is present in excess.
Okay, what I'd like to do here is go through these amounts, these different amounts, and we're going to predict how much NO2 are we going to make. We're also going to predict how much of the excess is left over, and that is a step that really confuses students. So first thing we're going to do is determine the limiting reactant in each scenario, and I'm going to start with this one that's just done, even though you've seen it happen. We are going to then determine the amount of NO2, how many NO2 molecules. Now remember, those coefficients mean molecules and moles. In this case, we're going to use them as molecules. Wouldn't be any different if you were in moles. And then 3, how much excess is left over. Okay? So we're going to go through that with this very simple example. You'll see what happens as I click on each one, and hopefully the process will be clear to you. All right, so in this first example, we had 4 NOs, we had 4 O2s. Using the steps that I've given you, 4 divided by 2, we would get into moles first. That's why it's step 2B when you have a limiting reactant. How do you know you have a limiting reactant problem? Limiting reactant problems are evident from having amounts for 2 or more reactants. Then you have to figure out which one am I going to use. Okay, so that's how you know you have a limiting reactant problem. All right, now, this is what this is all about, this animation. Okay, so I'm in moles, or in this case, I've counted molecules, same difference. 4 divided by 2 is 2. 4 divided by 1 is 4. This is a smaller number. This makes it the limiting reactant. Okay? Now, I don't use that number that I got when I divided. In fact, I don't even like to write it down. Now, when you get to some of the problems, you might have to write it down, but write it down small and off to the side. Okay, Now I'm going to determine how many NO2s using our same old process, taking that amount in molecules this time, but you'd be in moles normally. 4 times coefficient of what I'm moving to, 2, over what I'm coming from, 2, and that's why we made 4 molecules of NO2. Okay? All right, now how much of the excess is left over? This step always confuses students. Go back to limiting reactant. It determines everything. Okay, so you're going to go back to here, and we're going to move to the excess. 4 times 1 over 2 tells me how many, use mole ratio to determine amount used. Okay, so 4 divided by 2 is 2. I used 2 molecules of O2. Subtract to get how much is left over. In this case, it's 4 minus 2 equals 2 molecules left over. Or if you're in moles, you'll be doing in moles. Okay, left over. All right, so we're going to do this step 3 more times with these other 2, and then we'll check them after we've done our 1, 2, 3. Okay? All right, so let me erase this right here, okay, to do the next scenario, and then we'll click on it and see, if we see it in action. Okay. All right, so new scenario. All right, 6 molecules of NO, 3 molecules of O2. 6 divided by 2 is 3. 3 divided by 1 is 3. So I've got the exact stoichiometric ratio. Neither one is limiting because I get exactly the same number. You see, this is 2 to 1, so 6 is 2 times 3. So it doesn't matter which one I use, I will always figure out the same, I'll always get the same amount of the product in this case. So 3 times 2 over 1, I will make 6 molecules of NO2, and I will have nothing left over of either one because I don't have a limiting reactant or an excess. So let's click on the button and see if we are indeed correct.
Nitric oxide and oxygen gas are reacted in a 2 to 1 mole ratio. There are 6 molecules of NO in the left bulb and 3 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 6 molecules of NO are reacting with 3 molecules of O2. They are reacting in a 2 to 1 mole ratio as represented in the balanced equation. No reactants remain after the complete reaction.
Right? Let's go ahead and do this last one. 6 molecules of NO, 2 molecules of O2. 6 divided by 2 is, now if we were in a real problem, we'd have to make sure we were in moles. 6 divided by 2 is 3. 2 divided by 1 is 2. This is the smaller. This is my limiting reactant. All right, so we've done step 1. Step 2, how many molecules of the product have to use a limiting reactant? Times 2 over 1. 4, I will make 4 NO2s. Okay. How much of the excess is left over? Go back to the limiting reactant, move to the excess using the mole ratio, times 2 over 1. That tells me how many I use. I use 4, okay, because 2 times 2 is 4. I subtract to get the amount left over. All right, so I should have 2 molecules of NO left over, use up all the O2s, make 4 NO2s.
Nitric oxide and oxygen gas are reacted in a 3 to 1 mole ratio. There are 6 molecules of NO in the left bulb and 2 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 2 molecules of O2 are reacting with 6 molecules of NO. The 2 molecules of O2 only require 4 molecules of NO for reaction. Note the 1 to 2 mole ratio in the balanced equation. Therefore, 2 NO molecules remain after the reaction. The reaction stops once the oxygen gas runs out. O2 limits the amount of product that can be formed and is therefore called the limiting reagent. Nitric oxide is present in excess.
All right, so there are 2 NOs left over. We made 4 NO2s. All right, the process is really pretty simple. Get both your reactants, or if you have 3, get all of them in moles, divide by the coefficient to figure out which one is limiting, and then use it to figure out everything else in the problem, including how much of the excess is left over. You use the limiting reactant to figure out how much of the excess you use, and then subtract. Okay, I think that's a lot easier than doing this. All right, so let's do some problems from the notes. For the reaction shown, find the limiting reactant for each of the initial quantities of reactants. So I'm going to put in a little space here so I can write underneath. Okay, and now we are going, now all of these are in moles, so that makes it nice and easy. So 1 mole of chromium for A, 1 mole of oxygen. Okay, 1 divided by 4 versus 1 divided by 3. I'm in moles, so I can go ahead and do this step 2b. So 1 divided by 4 is the limiting reactant for A. Okay, so what I'm going to do is identify those by putting that over, and then I will erase, okay, to do the next one. All right, B, 4 moles of chromium and 2.5 moles of oxygen. 4 divided by 4 is 1. 2.5 divided by 3 is going to be smaller than 1. So this is my limiting reactant. Okay, so oxygen is limiting in B. Okay, so I don't even have to go through the math. I mean, for some of it, I can just know which one is smaller. All right. C, we have 12 moles of chromium and 10 moles of oxygen. 12 divided by 4 is 3. 10 divided by 3 is 3.33 something. 3333. So chromium is the limiting reactant in C. All right. And then our last one, 14.8 moles of chromium and 10.3 moles of oxygen. Can I do this without a calculator? No. All right, so 14.8 divided by 3, 4 is 3.7. So I hate to write it down because I won't use it. That's why I don't like writing it down. 3 points, oh no. So 3.7, okay. And 10.3 divided by 3 is 3.4. So this is my limiting reactant, this one, okay. So I'm going to erase those numbers because I don't want to mess up and use them, because I'm still going to use the 10.3 to do any other question in the problem. Okay? All right. I want to scroll a little bit and get rid of all that. All right. Next one. Why don't you pause the video and try this on your own, because actually I don't need the spaces here. I need them underneath the equation. Okay, I think what you will have seen when you print the notes out this time is that after I've done the video, I copy and paste the document back into the notes so that the spaces are there in the right places. So hopefully that has helped you. Okay, 2 moles of titanium and then 2 moles of chlorine. Okay, so 2 divided by 1 versus 2 divided by 2 is 2 divided by 1 is 2. 2 divided by 2 is 1. So this is my limiting reactant in A. Okay. B, 5 moles of titanium versus 9 moles of chlorine. 5 divided by 1 is 5. 9 divided by 2 is 4.5. So chlorine again is the limiting reactant. I would use the 9. .483. This is more like the kind of numbers you're going to get in a problem. 0.911. 0.483 divided by 1 is a larger number than 0.911 divided by 2. This is going to be like 0.45 something. So this is again my limiting reactant. Then one more, and this is true to form for your textbook. This last one will switch it up and titanium will be the limiting reactant. So 12.4 moles for the D, 15.8 moles for D, and for chlorine, and no, they did not switch it up. 12.4 divided by 1 is larger than 15.8 divided by 2. Chlorine, again, is the limiting reactant. Okay? So all we're doing there is we had a balanced chemical equation. Our amounts were in moles. We were dividing by the coefficients to determine the limiting reactant. The problem from there on is the same as what we've done in the previous lecture. All right, so here's a real limiting reactant problem where you were not given amounts in moles. All right, so let's write down what we have. We have 42.9 grams of this, and we have 6.86 grams of this, and they want to know how many grams of HF will be produced. So the first thing you've got to do is get both of these into moles. All right, so periodic tables at the ready. All right, so we have got to add up our molar masses from the periodic table, so that's what I'm going to do. Right now I am going to be writing those on top of the subspecies, the substances in the equation. So I'll be writing the molar masses on top. That way if I make a mistake, I can always go back. Now I know that this is 18.02, so I'll go ahead and put that one up there. And then let me go ahead and add up the others. Let me do that one again. Okay, I get 62.05 for the molar mass of the CH3COF, 62.05. All right, and then HF will be 19.01. All right, so all I've done is add up the masses from the periodic table. This equation is balanced. Yes, 2 H's. Okay, so now take your 42.9. This is a mole chart step divided by that 62.0. I can't even read my own handwriting. 702. Zero 0.691 moles is what I got for this one. Okay, 6.86 divided by 18.02. And I get 0.381 moles of, the H2O. All right, this divided by 1 versus this divided by 1. Obviously, this is my limiting reactant and is the one I must use. I am now in moles, and so everything from this point on is the same. So it's the complete box times 1 over 1. So I have the same moles of the HF, and now I'm under HF, so this is what I'm going to use its molar mass to convert back to grams. And that's not 19.01. Yes, it's 20.01. All right, so I messed up there. 20.01 for the hydrogen and the fluorine. So let me do that one more time. And that is 7.26 grams of HF. All right. Get them into moles, divide by the coefficients to see which one is limiting. From there, it's pretty much the same. We only have one thing to add to today's lecture, and that is percent yield. One more problem before we get into percentage yield. Okay, so 29.4 grams of hydrogen were reacted with 740 grams of chlorine. How many grams of HCl will be produced? Okay, convert them both to moles. And I'm going to need molar masses for everything. So this is, I'm going to go with 2.02, 70.9 for chlorine, and 36.46 for HCl, because I'll need that later. All right, so 29.4 divided by the 2.02. And I get 14.55 moles. Okay, 740 divided by 70.9, and I get 10.44 moles of the chlorine. Really looked like it was going to be the hydrogen, didn't it? But it's not. The limiting reactant is the chlorine. Okay, so I'm going to use it. This is the limiting reactant. I'm going to use it to figure out my HCl. 2/1 is my mole ratio. So 10.44 times 2, and I end up with 20.87 moles of HCl. And then there's my molar mass times the 36.46 grams per mole from the periodic table to convert back to grams. And I get 761.1 significant figures. I'm going to go with 3 significant figures is good, so 761 grams of HCl. Okay. All right, last thing to talk about in this lecture is percentage yield. And it is a step that actually happens at the end. So we've just introduced a little sub-step at the beginning, step 2b, and step percentage yield is just, you do that after you've done the problem. Before I leave this, let me just say that what we have just calculated and what we have done every time we have calculated a problem so far is we have gotten what is called the theoretical yield. That is the yield on paper that if everything were perfect, that's what you would get. Okay? Well, the world is not perfect, and you often get something different. And we call that the actual yield, what you actually get in the laboratory. So percentages are always part over the whole, so it's what you actually get in the lab. Usually it's less than the theoretical, it's not always. So actual over theoretical times 100. Now, you will either be given this in the problem, or you will be given the percentage yield. You are never given the theoretical yield. You are expected to do the stoichiometry problem. Okay? So you always have to do that. So that's nothing different. You're going to do exactly the same thing we've been doing. But then at the end, you'll calculate a percentage yield. All right? Okay, so here's a problem. 63.1 grams of HCl reacts with 17.2 grams of oxygen. 49.3 grams of chlorine are collected. So this right here, you being given something about a product and then being asked about a percentage yield, means that what they gave you in terms of the product is the actual yield. And you will not use that till the end. One thing I did not mention above is percentage yields are about products, about making products. Okay, so if you were given an amount of a product, then that means you've been given the actual yield. And they're asking you here to determine the percentage yield after you found the limiting reactant and the theoretical. Okay, so this is how this second sentence here with the stars, how it's actually worded in your textbook. Determine the limiting reactant, which you would do first, because you have been given amounts for two reactants, convert them both to moles. You then have to do the theoretical yield, and then you can get the percentage yield using this actual yield you've been given. However, I just want to point out that an alternative way of asking the same question is, what is the percentage yield for this reaction? So they're being nice in leading you to, to doing this limiting reactant part first, then do the theoretical, and then do the percentage. They didn't have to do that. And you may see questions where they leave that out. It is assumed you know to find a limiting reactant. What you were given regarding chlorine is the actual blah, blah, blah. So again, how do I know I have a limiting reactant? When I am given amounts like this for two or more reactants. Convert them to moles. If you're not in moles, get there. And then I will determine the amount of chlorine. How did I know it was chlorine? Because I was given information about chlorine. This is going to be my theoretical. And you have to do this every time. And then at the end, we'll combine these two to get the percentage yield. Okay? So, HCl, periodic table, 36.46, 32 for oxygen. So 63.1 divided by 36.46 moles of HCl are 1.73. Okay? 17.2 divided by 32, 0.538 moles of oxygen. 0.538 divided by 1, is that a smaller number than 1.73 divided by 4? 0.4, when I divide by 4, I get 0.433 here for HCl. Don't want to write it down because I'm not going to use that number. This is my limiting reactant. I get a smaller number when I take the amount in moles divided by its coefficient versus this one. All right, so I have to use this to calculate the grams. Now I'm already in moles times the coefficient of what I'm moving to over what I'm coming from. So 1.73 divided by 2 is 0.88 moles. Now on a multiple choice test, 0.88 grams would probably be one of the answers. Well, it's a percentage yield, so maybe not. Okay, so 0.88 moles and 70.9 was my molar mass for Cl2. So 0.88 moles times 70.9, 62.39 grams is my theoretical yield. At any point, if you don't understand how I got the numbers, stop the video, try it yourself, okay? Back up, go through it again, all right, to make sure that you understand where all of the numbers come from, all right? So percentage yield is actual over theoretical times 100. So 49.3 over 62.39 times 100, and that's our percentage yield. And I get 79.01 or 79%. Okay. Scrolling, which means I will lose that. All right, we've got two, and then two more problems to make sure we understand this process. All right, so 27.5 grams of N2H4. I mean, before I even read the problem and get that deer, and this goes for you, get that deer caught in the headlights look, I'm writing down the information as I read it. Calculate the masses of all reactants and products. So that means you're going to find out how much of the excess is left over once the reactants have reacted as much as, hold on, I'm going to lose that, darn it, as possible. Okay, so I have to figure out my limiting reactant. Now this is not a percentage yield question per se, but we do need to have, there we go, yay, to have practice with that whole excess thing. So convert them both to moles, so I can figure out my limiting reactant. I will use the limiting reactant to answer these questions, and then I'll figure out how much of the excess is left over. All right, so N2H4, 32.04 into O4, 92, 18.02, and 28. Just writing all my molar masses on top. So 27.5 divided by 32.04, and I get 0.858 moles. Okay. 74.9 divided by 92, and I get 8.814. All right, so 0.814 divided by 1 versus 0.858 divided by 2, this is my limiting reactant, and I must use it to figure everything out. So let's go ahead and do the excess first, since it's right there. So go to your limiting reactant, move using the mole ratio, 1 over 2. What I'm moving to, 1 divided by 2. 0.429 is how much I'm using. This is, when I do this, I get how much I'm using. I automatically put in subtract, because I'm going to subtract that from my original amount. And I get 0.385 moles left over. And if I want to put that in grams, I go ahead and just multiply times the 92. See how nice having it there up top. I needed it again. And I get 35.42 grams left over. Okay. Figuring out my products, I have to use the limiting reactant. All right. So 0.858, I'm going to do it down here. 0.858 moles times 4 over 2, okay, to get your amount of H2O. And I get 1.716 moles, and then times the 18.02 to get my grams, okay. So 30.92 grams of water is my amount of the water. Now I can use these moles here. I've used the limiting reactant, so I can just use the water to get the nitrogen. So times 3 over 4. And I get 1.287 moles of the nitrogen, and then times the 28 grams per mole. Okay. I end up with 36.04 grams of the nitrogen. Okay. That's pretty much as complicated as it gets. All right, one more, and we're done with this lecture. All right. For the balanced equation shown below, if the reaction of 19.8 grams of sodium produces a 55.9% yield, going to save that to the end, how many grams of Na2O are produced? Now, what they are asking you here is not what the theoretical yield is. They are asking you for the actual yield, okay? But you're given the percentage, so we'll be able to figure that out. First thing you got to do is get the theoretical. Convert this to moles. All right, sodium is 23, and I'll be doing this over here, so that weighs 62. Okay, 19.8 divided by the 23, and I get 0.861 moles. All right, of the sodium. This is not a limiting reactant problem. It's just a percentage yield. Move to the question, times 2/4, so dividing by 2, and I get 0.430 moles of the sodium oxide. Okay, and then times the 62 grams per mole. All right, and I get 26.69 grams of the sodium oxide. This is my theoretical. Okay, so 55.9 equals x over 26.69 times 100, bringing the 100 over, dividing both sides. I end up with, I'm going to move over here to the left, 0.559 equals x over 26.69. Cross multiply and divide. Okay, so times 0.559. 14.92 is my actual yield. Okay, now some of you smarties out there may have realized that if this is the maximum amount you can make, all you have to do is multiply it times the percentage in decimal form. And that's really all you have to do. Okay, this concludes lecture 14. I've tried to keep the lectures in this material smaller, so that we have more time in class and on sapling and so on to master these topics. They're not in themselves hard, but they do need some practice.